Okay, so today we're going to be proving the dot product. Right? So say you have a vector here. And the length of this vector, which this vector is A, the length of this vector is the magnitude of A. Now say you have a vector B. The length of this vector is the magnitude of B. Right? Now say we draw an imaginary line. And we have a right triangle here. Right? We know that this length here is the magnitude of B times the cosine of the angle theta. This angle theta here. Right? We also know that this length here is the magnitude of B times the sine of the angle theta. Right? You'll see why I'm doing all this in a minute. Now let's say we have another line here. Right? Y'all see that one? And this length, if you know vector addition and vector subtraction, then you know the length of this vector is the magnitude of A minus B. Now, in order to prove the dot product, right, we have to solve for this term here, the length of this side. Well, actually, the length of this side squared. Right? We'll solve it in two different ways. And then we'll compare those results. The first one is by using the Pythagorean triangle. Because clearly, the length of this right here, from here all the way to here, is going to be this term here minus this term. So we get the magnitude of A minus the magnitude of B cosine theta. Now, we can set up a Pythagorean triangle and solve for our term A minus B squared. The other way is by components. And by components, I'm just going to use the classic three-dimensional vectors, and I'm going to label the components of A as A is equal to AXI plus AYJ plus AZK. Or okay, so now that we have that, everybody just remember this picture. I don't have much space on the whiteboard, but let's get into it. This is one of my favorite things to do. Haven't done it for a long time. I mean, it's a tedious task. It might take it won't take too long. But anyway, so the first one we'll do in blue. So we said that we have our triangle, and go back and correct me if I'm wrong. Please do. So we have A minus B squared is equal to Let me move it over just a little bit, since you can see the whole side of this board. A minus B squared is equal to the magnitude of A minus the magnitude of B cosine theta squared plus the magnitude of B sine theta squared. Right? Okay, so let's solve. Now, A minus B cosine theta squared, this is going to give us, right? It's going to give us the magnitude of A squared, right? Minus 2 magnitude of A, magnitude of B, cosine theta, right? Squared. Magnitude of B cosine squared theta plus magnitude of B squared sine squared theta. Right? Now this term is important. That's why I got a little excited. Because as you see, we have our first trig identity. You know, these come from Moiré theorems. But anyway, cosine squared plus sine squared is equal to 1. So that means we have A minus B squared is equal to the magnitude of A squared plus the magnitude of B squared minus 2 magnitude of A, magnitude of B, cosine theta. All right, cool. The first part's easy. So just remember this. I'll move it up here. Right? This is 1. Or I'll call it money 1. Yeah, you like my symbols. Okay, so money 1. We'll just rewrite it all the way up here. Okay, y'all might not be able to see that, but don't worry, I got you. So the second one we'll do in green. We'll do this component-wise. And remember, I told you I haven't done this in a long time, so forgive me for my pauses and my hesitation sometimes. All right, so, and I'm just a person recording these by myself. A minus B squared, component-wise, is equal to, let's see, it would be the x term, or the I term from here, all right? Which I would label as x, right, like I said. So we get the ax minus bx squared, right? Plus ay minus by squared plus az minus bz squared. Right? Because this is the magnitude of a vector. What I'm trying to say is if vector r is equal to x comma y comma z, then the magnitude of r, right, is equal to the square root of x squared plus y squared plus z squared. Based on that, the right triangle situation, right? So if we square that, we square any magnitude, we just get this leftover component squared, right? And its components are ax minus bx, ay minus by, az minus bc. Can y'all see the green? Right? And let's solve. So ax minus bx squared, we're going to get a ax squared plus a bx squared minus 2ax bx. Plus similarly with this one, ay squared plus by squared minus 2ay by. Same thing with this one. I'll write it here. Plus az squared plus bz squared minus 2az bz. BZ, like Beazle. Shout out to Biggie. Okay, so now that we have that, right? Now let's think. We can combine a few terms, right? Now we see we have a ax squared, ay squared, and an az squared. I believe that is equal to the magnitude of a squared, right? Similarly with b. Right? And all that's left over is 2 times ax bx, right? Plus ay by, right? Plus az bz. My mans. Right? Forgot my equal sign. Don't forget your equal sign. Bam, that's looking pretty good. Now you remember money 1? Now that we got money 2. Now let's compare our pocket change. You know, I got 1 pocket, you got 2 pockets, I got $3, you got 5, I got 7, you have 9. We're just gonna put them together and we're gonna make some money, man. All right, so I'm gonna put them together with this burgundy, So let's erase all this middle stuff. Let's move money 1 back down. So money 1, the term a minus b squared was equal to the magnitude of a squared plus the magnitude of b squared minus 2 times the magnitude of a, magnitude of b, cosine of theta. Now, as you can see, for money 1 and money 2, that these two terms are equal, right? Because they equal this. Right? So now we can cancel out these. Boom, boom, boom. And all that's left over is a negative. Oh, we can also get out rid of this negative 2. All right. So all we have left, the dot product. There you have it.